Hi everyone, today we're doing trigonometric identities continued. So you should have already done the introduction to 5.5 and watched the video and done the work there, or today you're going to find today pretty confusing. So if you haven't done that yet, you need to go back and do that. So these are some identities we already know that we got from our last lesson. The Pythagorean identity, that's the big one. That's one you've got to memorize. It's the most important one, and the explanation comes from last lesson. Remember that an identity is a mathematical statement that is true for all values of the given variables. So something is an identity if no matter what you sub in for theta, you're going to, in this one, you'll get it to equal 1. But an identity means the left side is going to equal the right side no matter what you sub in. So these are already your textbook, and they're ones that you already know, right? You already know that cosecant is 1 over sine and all that. So we already know the reciprocal identities, so they're all true. You can use those in any of your questions today. You can, if you have a question with cosecant in it, you can change it to sine. Usually we do that. Usually we prefer to work with sine and cos in our identities rather than cosecant, secant, or even cotangent and tangent. So we also know that tan is sine over cos, and then if we flip all that over, we get cotan is cos over sine. Now this is the big Pythagorean identity, sine squared theta plus cos squared theta equals 1. Now there's two more here, two more Pythagorean identities. So they just come from taking the original one. So I'm going to take sine squared theta plus cos squared theta equals 1, and I'm going to rewrite it as sine squared theta plus, so you don't have to memorize these two here. You can just derive them. So if I can't remember the other ones, I'm going to divide everything by sine squared theta here. Divide everything by sine squared theta. And sine squared theta over sine squared theta is 1. Cos squared theta over sine squared theta, that's here, right? Cos squared theta over sine squared theta is cotan theta squared. And then 1 over sine is cosecant. So that's this one here that I just proved. So if you know the main one, you can figure out the other ones. You would do all this again, but divide all three by cos squared theta, and that would get you the second one here. So this is the big one to know. If you have this one memorized, you can get the other ones just by rearranging it. We are going to learn how to apply some of the skills we already have with algebra, like factoring, distributing, and apply those skills to proving trig identities. So the great thing about math is once you know a skill like factoring, you can use it all over the place. First thing we're going to talk about are common denominators. So think back to elementary school. If you had 2/3 plus 5 and you wanted to add them with a common denominator, you'd have to first find the lowest common denominator. In this case, it would be a 3. All right, so that's already a 3. That's not. So this is 2/3. This is okay, but I need to convert 5 to something over 3. So 5 is already over an invisible 1. So whatever I do to the bottom, which is multiply by 3, I have to do to the top, multiply by 3. I get a 15. So now I can add them because they have a common denominator. We can do the same thing with trigonometric ratios. So this is an alpha, tan alpha plus 1 over tan alpha. So what's the lowest common denominator here? The lowest common denominator here is going to be, so this is over an invisible 1, right? So this, our lowest common denominator is going to have to be our only denominator, just like in the question we did over there. It's going to be tan alpha, just like the previous question, it was a 3. So we have a tan alpha there, and a tan alpha here. This one's okay, it's already a 1. But this one, I had to multiply the denominator by tan alpha. Means I'm going to have to multiply the numerator by tan alpha. So I'm going to get tan alpha times tan alpha is 10, and you put the squared here, tan squared alpha. So I put those two together, I now have a common denominator. My common denominator is tan alpha, and I have tan squared alpha plus 1. So this question just said to simplify So I don't have to go any further with that. It just says simplify by finding common denominator. But if you look on the previous slide, you could see that I could go further. I could still simplify that a little bit more. But this is just practice, getting you to practice finding a common denominator here. So we don't have to state restrictions. They do exist, but in this course we don't have to state them. So we would have, we would say tan alpha cannot equal 0. When is tan 0? That you don't have to worry about any of that. I'm not going to ask you for restrictions. And if the textbook asks you for restrictions, you can skip it. Reverse common denominator. So let's say you were in elementary school and you had this line. What would you have had above it? What would have been right here? What would have been the step above it? So above that, I would have had 3 over 2 plus 7 over 2. That would have led to the next line, right? So that's kind of a reverse common denominator that we need to sometimes. We split the denominator. In this case, I'm going to split the denominator. Look at the one that I just did. So I want you to press pause and do what I just did, but with sine squared. Okay, hopefully you've done that. So I'm going to split the denominator. I'm going to take my denominator of sine squared and split it up as if I were going one step backwards from where I was. The step before this step would have been sine squared theta minus 1 over sine squared theta, right? That would have been the step before if I would have had that. So I can simplify a little more because I know that these two are the same. Sine squared theta or sine squared theta are identical. They're equal to 1. And I could, if I wanted to, it just says simplify here. I don't really have to keep going any further, but I know that 1 minus sine squared theta, for example, is cosecant squared theta. So I could keep going like that. There are questions in your textbook, specific questions that just say simplify. And this is all they want you to do. They just want you to practice. I didn't assign any of those questions, but for sure you can do them. They're not proofs, they're just simplifying. They're just getting you to practice things like common denominators and factoring. So example 1, prove, let me see if I can clean this up a bit. Okay, I'm going to prove 1 plus tan squared theta equals secant squared theta. Remember that we have to prove on the left side, right side format. So I'm going to work with this side separately than I am with the right side. There, I've put a big space in between them, and you have to do that too. You cannot put them together because we can't say, oh, I'm going to subtract 1 from both sides and bring it over. You're not allowed to do that for a proof. So this is actually one of them I just talked about on a previous slide. It's a variant on the Pythagorean identities. This actually is in your chart there, but we're going to prove where it came from here. So let's go to first the left side. It says over here on the right, work with one side at a time. We're going to work with the left side first because that one looks to be a little more complicated. Work with one side at a time. So I'm going to start working with the left side. I'm going to try to make it look like the right side. We're going to use the quotient identity and what we already know about reciprocal functions. So the quotient identity, hopefully you remember that one. So 1 plus tan squared theta. I can't use that. I can't just say that that's equal to secant squared theta because I have the proof. I have to prove it this time. So I'm going to change. It's always better if you can to put everything in terms of sine and cos. So I'm going to change this one instead of tan squared theta to sine squared theta over cos squared theta. So here I'm at my common denominator situation. I want to put these two together with a common denominator. The common denominator would be cos squared theta. Cos squared theta. So this one's already fine. This numerator is going to stay sine squared theta. But this one, this is a 1 over a 1. If I've multiplied my denominator by cos squared theta, I have to multiply the numerator by the same thing. So it's cos squared theta. Right? That makes sense. 1 is the same as cos squared theta over cos squared theta. So I have a common denominator. My common denominator is cos squared theta. And my numerators, now I can put them together. I've got cos squared theta plus sine squared theta. And hopefully there's some bells going off in your head now. This is what I like about identities, is you're not doing a whole lot of math. You're not doing calculations and what quadrant should this be or all that. You're just putting a bunch of puzzle pieces together. So right now there's something that should be really familiar about that. Really familiar, especially about the numerator. Look at that numerator there. That should ring a bell for you. The most important identity we have is the Pythagorean identity that says cos squared theta plus sine squared theta is equal to 1. So we get 1 over cos squared theta, which if you look at the right side, that's exactly what secant is. So I could change that to 1 over cos squared theta. So they are exactly the same. Remember a statement, either left side equals right side, or you can write QED, because you proved it. You just proved that this is true. Another strategy we have is factoring. So again, we already know how to factor from grade 10 for sure. Factoring here, this is a sum and product question, so I need two numbers that have a sum of -5 and have a product of 6. So those numbers are -2 and -3. This is an easy trinomial, which means I can just write these numbers directly into my brackets. So I'm going to have the square root of this at the front, so I'm going to have x's. And then these two numbers go in the brackets, x minus 2, x minus 3. So that's a review of factoring. We have the same, we're going to use the same strategy for trigonometry. So right here, this one though, it's not a trinomial. I see that I have a greatest common factor. The greatest common factor here is cos. So this term here and this term here, they're separated by a plus sign. That's how I know those two are separate from each other. So if I factor out a cos out of both, I will be, oops, sorry, that's not an equal sign. That should be a bracket there. I'm left with cos theta plus sine theta. And the question just said simplify by factoring, right? This wasn't a proof, this is just simplifying. So this is just practicing how to factor. So that's how we take out a greatest common factor. But we can also factor like the trinomial we did above. So looking at this one, it again says simplify. We're not proving it, we're just practicing our skills here. So here's a strategy. If we let A equal cos and B equal secant, that maybe helps us to clean this up a bit, because when we look at this question, it looks very confusing. So I'm just going to change all the coses to a's. So this one's going to be an a squared. There's another cos, that's minus a minus 2. The denominator will be, so I've got a secant multiplied by a cos, so that's going to be a times b or b times a, but I'm going to put it alphabetically. A times b plus, and then the secant here, that's a b. Okay, so we take a look at what we have here, and I've got a trinomial in my numerator. I can factor that trinomial. A minus 2, a plus 1, and my denominator has a greatest common factor of a b. So I take the b out, and I get a plus 1. So it's fine to use this strategy, but just make sure once everything's factored, you then eventually put everything back into sine and cos. So I can do one more thing here before I put it back to secant and cos, I should say. These, remember from our factoring, these are binomials here that match completely. They're exactly the same, a plus 1, I can cancel them out. So these are exactly the same. So they cancel out, so I'm left with a minus 2 over b, or putting it back the way it's supposed to be, a is cos theta minus 2 over, and b is secant theta. So that is both types of factoring in one question. Here we are on our last example of proving. So we're going to do a proof here. We have to prove that this ugly thing is equal to this, right? I've got a new Greek letter in here for you. It's called phi. It's pronounced F-I, phi. This is where we get our PH sound in English, like phone, or elephant, where the PH that makes an F sound comes from this Greek letter here. So it rhymes with pi, but it's spelled phi. Anytime you get a different Greek letter, you can change it back to theta. Students tend to do that a lot. They are more used to theta than anything else. So if you change it to theta, it's fine. It doesn't matter. Tip, always start with the most complicated side first. So in this one for sure, I would be looking at this side. This looks a lot more complicated. Since there's only one squared portion, right? So this is the only thing that's squared. So, and I have to make it look like this one. There's nothing squared on this side. So I don't want anything squared over here because I'm not going to end up with anything squared on my right side. So I'm going to try to eliminate it, and I'll show you what I mean by this last step here. So, all right, I'm looking at the left side first. Remember to set it up properly. When you do a proof, you have a left side and you have a right side. So my left side is sine squared phi over 1 minus cos phi. And on the right side, I've got 1 plus cos phi. And as I pointed out, I've got one term that's squared, but nothing else is. So I'm going to get rid of that squared. I'm going to use the Pythagorean identity. Pythagorean identity is, in short form, sine squared theta plus cos squared theta equals 1. So I'm going to isolate sine squared theta by bringing cos squared theta over this side, which means instead of sine squared theta right here, I'm going to write 1 minus cos squared phi over 1 minus cos phi. So how does that help us? We still have a squared, but the difference is everything is in coses now, which is good because this is right. Keep your eye on the prize. I always want it to look like this. I always want it to end up like this. So at least I've got everything in the right terms here. So I'm going to factor by using difference of squares. So this numerator, you can change it to 1 minus a squared if you want to, the numerator, if it makes it a little easier for you to see. I'm going to leave it this time, but you can factor it. You can change it to a. So this is a difference of squares. So that means I set up two brackets, one with a plus sign, one with a minus sign. The square root of the front term goes at the front. The square root of the back term goes at the back. That's just going to be cos phi. There's cos phi there. And I'm dividing it all by, I can't do anything about that denominator, right? Don't think, oh, that I'm going to use Pythagorean identity there. This is not squared. If it's not squared, you can't use Pythagorean identity. So I can't do anything with this denominator here. So I'm going to leave that alone, 1 minus cos phi. But hopefully you see something and put brackets around it to remind myself this is a binomial. Hopefully you see something that we can do here. And if you do see that, look over to your right side and you'll see that we're done. We really solved it. These binomials are exactly the same as each other. They cancel out. I'm left with 1 plus cos phi, which is exactly my right side. So QED, we got our left side to equal our right side, and it all, even though when we started it out, they looked very, very different from each other, as they always do in these questions. You think, how am I ever going to make this mess look like this? But if the question says prove, then it's going to work. If I said to you, is this a proof? Well, that would be really tough because then you could spend all day working on it. But if it says prove, then it means it's going to work. You have to prove it. And you have to prove it doing one side, the left side, and then doing the right side separately. That's it. You can't put them together. So that's the end of your lesson today. Your homework are these questions right here. Good luck. I hope you enjoyed them. I really like doing trig identities because it's just putting all the puzzle pieces together. You might want to make a sheet up with all the little formulas that you have so you can switch back and forth easily.